What if I told you that right now, as you're watching this, a machine is listening to the whispers of reality, decoding the fundamental language of the universe in a way we've only ever dreamed of? Friends, welcome. I want you to take a moment and think about the most powerful computer on the planet. Picture it. A machine filling an entire room, humming with an almost unimaginable power, capable of trillions of calculations per second. Now, imagine something so far beyond that, it makes that supercomputer look like a child's abacus. Google has just pulled back the curtain on a technology that does exactly that. It's called quantum echoes, and it's running on their groundbreaking Willow quantum chip. The numbers are staggering. It's not just a little faster, it's 13,000 times faster than the world's reigning supercomputer champion. But this isn't just about speed. This is about a fundamental shift in our relationship with the universe. For the very first time, a quantum computer has produced results that aren't just a theoretical party trick. They are verifiable, repeatable, and confirmed against the very laws of nature. This is the moment science fiction bleeds into scientific fact. Let's really unpack that number for a second. 13,000 times faster. It's a figure that's almost impossible for our minds to grasp. Imagine you asked the world's fastest supercomputer to solve a problem so complex it would take it a full year, working nonstop, day and night. The Willow chip, running quantum echoes, would deliver the answer in under 40 minutes. What could you do with that kind of power? It's not just about getting answers faster. It's about being able to ask questions we never thought possible. But as I said, the true revolution here isn't the speed, it's the verifiability. Think of early quantum computers as incredibly gifted, but slightly eccentric geniuses. They could solve problems that no classical computer could touch, but their answers were often fleeting, shrouded in uncertainty, and impossible to double-check. It was like a mathematician who could solve an impossible equation but couldn't show you their work. You were left to trust that they were right. Google's quantum echoes changes the game entirely. The results it produces can be repeated on other systems. More importantly, they can be tested and confirmed against physical reality itself. This is the bedrock of all true science. A discovery, no matter how spectacular, is just a claim until it can be independently verified. With quantum echoes, quantum computing has finally earned its scientific stripes. It has graduated from a fascinating but esoteric field of study into a legitimate and powerful tool for discovery. For decades, the story of quantum computing has been one of immense promise, but that promise was always just over the horizon. Scientists were studying the quantum computer itself, trying to understand its bizarre behavior, its fragility, and its immense potential. It was like we had built a new kind of telescope. But we were so fascinated with the lenses and gears that we forgot to point it at the sky. This announcement from Google marks the moment we finally turn the telescope outwards. Quantum systems are no longer just the subject of our study. They are becoming the tools for studying nature itself. And what a tool they are! We're talking about a key that can unlock insights at the most fundamental level of reality. Everything around you, the chair you're sitting on, the air you're breathing, the complex dance of molecules within your own body, is governed by the strange and counterintuitive laws of quantum mechanics. Our classical computers, for all their power, can only approximate these laws. It's like trying to describe a symphony using only a few notes. A quantum computer, on the other hand, speaks the native language of the universe. It can simulate quantum systems directly, allowing us to see the world as it truly is at its most granular level. This isn't just an incremental step forward, it's a paradigm shift. It is the difference between reading a description of a distant planet and actually landing a rover on its surface. So how does this revolutionary technology actually work? The concept behind quantum echoes is both elegant and deeply intuitive, inspired by one of nature's own ingenious navigation systems: echolocation. Imagine a bat flying through a dark cave. It sends out a high-pitched cry, a ping, and then listens intently for the echoes that bounce back. From the timing and character of those echoes, it can build a detailed mental map of its surroundings, the distance to a wall, the flutter of a moth's wings. Google's team applied a similar principle to the quantum realm. They start with their system of qubits, the quantum equivalent of classical bits, in a pristine, ordered state. Then they run a series of quantum operations forward in time, like the bat sending out its cry. Next, they introduce a tiny, precise disturbance to just one of the qubits. This is the equivalent of a moth fluttering in the path of the sound wave. Finally, they reverse the entire sequence of operations, essentially uncomputing what they just did. In a perfect classical world, you'd expect to end up exactly where you started, with the system returning to its initial pristine state. But in the quantum world, things are far more interesting. The small disturbance they introduced creates a ripple effect, an interference pattern that spreads throughout the system. When the process is reversed, this ripple doesn't just disappear. Instead, it generates what they call quantum echoes, faint, ghostly signals that carry a wealth of information. These echoes are the returning sound waves for our quantum bat. By carefully listening to and analyzing these echoes, the scientist can map out the hidden landscape of the quantum system. They can see how information flows, how different qubits are secretly talking to each other, and how the delicate dance of quantum mechanics unfolds across space and time. It's a breathtakingly clever way to probe the invisible world. If the concept is so elegant, why hasn't this been done before? The answer lies in one of the biggest hurdles in quantum computing: noise. The quantum world is an incredibly fragile place. The slightest vibration, a stray magnetic field, even a tiny fluctuation in temperature can be enough to knock a qubit out of its delicate state and destroy the information it holds. This is what we call quantum decoherence, and it's the mortal enemy of any quantum computation. Trying to detect the faint signal of a quantum echo amidst this overwhelming background noise has been, until now, almost impossible. It has been likened to trying to hear a single whisper in the middle of a roaring football stadium during a championship game. The signal you're looking for is there, but it's completely drowned out by the cacophony of the environment. The data is lost, washed away in a sea of quantum static. This is where the sheer engineering brilliance of Google's Willow chip comes into play. Through years of painstaking research and development, they have managed to create a system with unprecedented precision and error control. The superconducting integrated circuits that make up the chip are designed to be as isolated from the noisy outside world as possible. They are cooled to temperatures colder than deep space to minimize thermal vibrations. But more than just passive shielding, Willow employs active error correction techniques. It's constantly monitoring its qubits, checking for errors, and correcting them on the fly. This ability to suppress noise and maintain the delicate quantum state, what S known as coherence, is the secret sauce. It allowed them to finally quiet the roaring stadium, enough to hear that whisper. And the scale of their effort is mind-boggling. They collected and analyzed 1 trillion measurements to cleanly capture this meaningful quantum data. It's a testament to the power of persistent, incremental engineering in achieving a revolutionary breakthrough. Let's take a closer look at the hero of this story, the Willow quantum chip. For decades, a frustrating bottleneck has plagued the development of quantum computers. It's known as the scaling problem. You could add more qubits to your processor, but with each qubit you added, the error rates would also increase, often exponentially. It was a classic catch-22. To build a more powerful computer, you needed more qubits, but more qubits meant more noise, which made the computer less reliable. It felt like trying to build a taller and taller tower out of increasingly wobbly bricks. At some point, the whole thing was destined to collapse under its own instability. The Willow chip represents a fundamental break from this frustrating cycle. Google S engineers have achieved a level of control over their quantum hardware that was previously thought to be years, if not decades, away. Their quantum gates, the fundamental building blocks of a quantum circuit, analogous to logic gates in a classical computer, are executed with ultra-high accuracy. Think of it as a master watchmaker crafting gears with microscopic precision. This accuracy is combined with intelligent, built-in noise reduction systems that actively preserve the coherence of the qubits. The result is a chip that can execute thousands of complex, intricate operations, a long and winding quantum algorithm, while keeping its quantum state intact. The tower no longer wobbles. This stability, this coherence, is the absolute foundation upon which the quantum echoes experiment was built. Without Willow's ability to maintain its delicate quantum state over a long and complex computation, the faint echoes would have been lost in the noise forever. This hardware revolution isn't just an improvement. It's a game changer that has unlocked a new realm of possibility for quantum computation. A groundbreaking technology is only as good as the problems it can solve. And this is where the story of quantum echoes takes a thrilling turn from the realm of theoretical physics and computer science into the tangible world of practical, real-world science. Google didn't just want to prove their machine was powerful, they wanted to prove it was useful. To do that, they partnered with researchers at the University of California, Berkeley, and set their sights on one of the most fundamental and challenging problems in chemistry: predicting the structure of molecules. They used quantum echoes to simulate two different molecules, one with a respectable 15 atoms and another, more complex one with 28. This is a task that pushes even the most powerful supercomputers to their limits. The number of possible interactions between the electrons in a molecule of that size is astronomically large. But for the Willow chip, it was a challenge it was built for. The team ran their quantum echo simulation and generated predictions for the precise three-dimensional structure of these molecules. Then came the moment of truth. They compared their quantum computer as predictions to results from a tried-and-true experimental technique called nuclear magnetic resonance, NMR, spectroscopy, a gold standard in chemistry for determining molecular structure. The result? A perfect match. The quantum simulation had accurately predicted the physical reality. It was a stunning validation of the technology, but they didn't stop there. In a truly jaw-dropping demonstration of quantum advantage, the quantum echo simulation revealed subtle details about the molecular structures, faint interactions, and quantum effects that were beyond the reach of even the sophisticated NMR methods. The student had become the master. The simulation was now teaching the experimenters new things about the physical world. Why all this focus on molecular structure? It might sound like an abstract scientific pursuit, but understanding the precise geometry of molecules is the gateway to solving some of humanity's most pressing challenges. Think of a molecule as a tiny, intricate key. Its specific shape determines what locks it can open. In the world of medicine, that lock could be a receptor on a virus or a cancer cell. If you can accurately predict the shape of a drug molecule, you can design a key that fits the lock perfectly, leading to more effective treatments with fewer side effects. The current process of drug discovery is incredibly slow and expensive, often relying on trial and error that can take years and cost billions of dollars. With a tool like quantum echoes, pharmaceutical researchers could digitally simulate countless molecular candidates, identifying the most promising ones before ever stepping into a wet lab. This could revolutionize the speed at which we develop new medicines, from antibiotics to fight superbugs to personalized cancer therapies. But it doesn't stop at medicine. The same principle applies to developing better batteries for electric vehicles and grid-scale energy storage. The efficiency of a battery depends on the molecular interactions at its electrodes. By simulating and designing new molecules, we could create batteries that charge faster, last longer, and are made from more sustainable materials. Think about the quest for advanced materials, lighter and stronger alloys for aerospace, more efficient catalysts for clean energy production, or even new polymers that can capture carbon directly from the atmosphere. All of these innovations hinge on our ability to understand and manipulate matter at the molecular level. Quantum echoes provides a powerful new lens through which to see and design this future. It has the potential to shorten research and development cycles from years to months, accelerating the pace of innovation across virtually every field of science and technology. Some of you might be thinking, wait a minute, didn't Google already achieve a quantum milestone a few years ago? And you'd be right. Back in 2019, Google announced that it had achieved quantum supremacy. This was a landmark moment where their Sycamore quantum processor performed a specific, carefully crafted mathematical calculation that was, for all practical purposes, impossible for even the most powerful classical supercomputer. It was a phenomenal achievement, a hello world moment for the age of quantum computing. However, the problem that Sycamore solved was by design an artificial one. It was a benchmark, a test to prove the hardware's power, but it didn't have any immediate practical application. It was like building the world's fastest car and proving it could break the sound barrier on a perfectly straight, empty salt flat. It's an incredible feat of engineering, but it doesn't tell you how that car will handle in city traffic or on a winding mountain road. The quantum echoes breakthrough is fundamentally different. This is a leap beyond supremacy into the realm of verifiable quantum advantage. It's not about solving an abstract math problem faster. It's about using a quantum computer to solve a real, scientifically meaningful problem, and doing so in a way that is faster, more accurate, and more insightful than any classical method. And crucially, the results are repeatable and can be checked against the real world. This isn't just flexing computational muscle. It's putting that muscle to work to measure and understand nature. This is the difference between a demonstration and a discovery. It is the moment the quantum computer gets off the salt flats and onto the open road of scientific progress. This element of verifiability cannot be overstated. It is perhaps the most important part of this entire story. For the first time, the results produced by a quantum computer are not a black box. They can be rigorously checked and validated through multiple independent channels. Another quantum system could be tasked with running the same simulation to see if it gets the same answer. Physical experiments, like the NMR spectroscopy used in the UC Berkeley partnership, can be conducted to see if the quantum predictions match physical reality. And finally, the results can be compared against established scientific theory. This three-pronged approach to verification, by other quantum systems, by physical experiment, and by theory, closes a long-standing credibility gap in the field of quantum computing. It establishes a new scientific standard for the quantum domain: reproducibility. Science is built on a foundation of trust, but the trust is earned through skepticism, rigor, and the ability of others to reproduce your results. By meeting this standard, quantum computing has officially come of age. It's no longer a fringe field operating on faith and theoretical promise. It is now a robust and reliable scientific instrument, ready to take its place alongside the other great tools of discovery. This breakthrough provides the confidence needed for the wider scientific community to begin embracing quantum computers as a legitimate and essential tool for their own research. History is marked by moments when a new instrument gives us a new way of seeing the world, and in doing so, changes everything. When Galileo pointed his telescope toward the heavens, he didn't just see points of light. He saw the moons of Jupiter, the phases of Venus, and the craters on our own moon. He saw a universe that was far grander and more complex than anyone had ever imagined. When Antony van Leeuwenhoek peered through his microscope, he discovered a hidden world teeming with life in a single drop of water, laying the foundation for modern biology and medicine. Quantum echoes represents a similar inflection point in the history of science. It is our telescope moment for the quantum realm. It is a new kind of instrument, a quantum scope that allows us, for the first time, to see the invisible reality that underpins everything. We can now directly observe the subtle and complex interactions inside molecules and materials. We can watch the flow of quantum information, trace the paths of ghostly echoes, and build a picture of a world that has, until now, been completely hidden from our view. Just as the telescope opened up the cosmos, and the microscope revealed the building blocks of life, this quantum scope is opening up the fundamental fabric of reality itself. What new discoveries will we make? What hidden laws of nature will be revealed? We are like the first astronomers, peering through a new lens at a universe of possibilities. The potential for discovery is limitless, and the journey is just beginning. So, with this incredible breakthrough, is the work done? Far from it. This is a profound and crucial step, but it is still a step on a longer journey. Google Edu's next major goal is to build what is known as a long-lived logical qubit. To understand what that means, let's go back to our noise problem. The physical qubits in today's quantum computers, like those in the Willow chip, are still susceptible to errors, even with advanced error correction. A logical qubit is a different beast altogether. It's an ingenious concept where you use a collection of many physical qubits to encode the information of a single, ultra-robust, fault-tolerant qubit. It's like having a team of scribes all writing down the same important message. If one scribe makes a small mistake, you can look at the copies from all the others to easily spot and correct the error. A logical qubit works on a similar principle, using the redundancy of many physical qubits to create a near-perfect quantum bit that is almost completely immune to noise and decoherence. Achieving a stable, long-lived logical qubit is often considered the holy grail of quantum computing. It would mark the birth of truly scalable quantum computers, machines capable of running vast, incredibly complex computations for long periods without succumbing to errors. This would unlock applications that are still firmly in the realm of science fiction today. But what the quantum echoes experiment so powerfully proves is that we don't have to wait for that ultimate milestone to start doing useful, world-changing science. It demonstrates that even with the noisy, intermediate-scale quantum NISQ devices we have today, we can achieve a verifiable quantum advantage for specific, important problems. Useful applications are already here, and they will only get more powerful as the hardware continues to evolve. The pace of progress in this field has been nothing short of exponential. It took decades of painstaking research to get to the point of quantum supremacy in 2019. In the few short years since then, we have made the leap to verifiable quantum advantage. So, what does the near future hold? Google has put a bold timeline on the table. Within the next 5 years, they expect to see the emergence of full-scale, quantum-enhanced applications, making a real-world impact in fields like drug discovery, clean energy, and materials science. This isn't a distant, futuristic dream. This is the tangible, near-term horizon. The story of quantum echoes is more than just a tale of scientific and technological triumph. It holds a powerful lesson for all of us. It's a story about the power of seeing the world differently. It's about being inspired by nature, like the bat's echolocation, to find elegant solutions to complex problems. It is a testament to the incredible things that can be achieved when relentless engineering is combined with a bold scientific vision. And most importantly, it teaches us that even the faintest whispers, the tiniest echoes, can carry the most profound secrets if we only learn how to listen. In our own lives, how often do we dismiss the quiet signals, the subtle intuitions, the whispers that get drowned out by the noise of our daily routines? This story reminds us to cultivate the quiet, to build our own internal error correction, and to listen for the echoes of truth that can guide us. The universe is constantly speaking to us in a language of echoes and patterns. The question is, are we building the instruments, both external and internal, to hear what it has to say? I'm left with a few questions, and I'd love to hear your thoughts in the comments below. If you had access to a machine that could listen to the whispers of reality, what question would you ask it first? And how do you think this new ability to see and manipulate the world at its most fundamental level will change what it means to be human? Thank you for joining me on this incredible journey today. I hope you found it as awe-inspiring as I did. Wishing you all the very best of health and clarity in the days ahead. And if you enjoyed this deep dive and want to stay on the cutting edge of science and technology, don't forget to hit that subscribe button and ring the bell so you won't miss what is next. Until next time,